Alright, time for another draftphysics.com video presentation. So the Ian Gosling guy has actually done an experiment sort of as I described this morning, which is kind of quick, and so that's good. And the results, okay, the preliminary observation is undeniable, really. I mean, we're just looking for a little weight down there in the first picture. That height, it is off the table. We're looking for 4 times that height in this other one. This is one way up here. Yeah, see, 4 times the height would mean twice the velocity falling in gravity. So it would be exactly as I predicted. So if it's 1 to 4 in terms of the height that it has risen, then it's proving, okay, that I just made free kinetic energy, that the experiment did that. And that the momentum is perfectly conserved and you made free kinetic energy. So as I've stated, it's a free energy formula, it's a free energy theory, and frankly the lever proves it, and it certainly proves it in this experiment. This looks like pretty good evidence. So, let's give it time. Let other people opine on how that isn't 4 times the distance, but there's no way I can see it as anything other than a lot more, okay, than 1.4. It's a lot higher off this table than, even twice. It's a lot higher than twice as high. So anyway, it'd be better if we had a better camera angle, all of that stuff. So maybe he can do it with a, lower the camera so we can see the height, and that'll tell the tale, really. It's about how high it goes up. The only thing stopping it from going forever, again, is gravity. And so, forever-ish. So gravity's telling you how much gravity, how much force it overcame. The story's being told by how high it goes. I guess I'll just illustrate that quickly, and we'll call it a video and see what the reaction is to what is a pretty good piece of evidence for my side, frankly. So I actually have to thank Ian for doing the experiment, because I really didn't want to have to do it. So now I won't. Maybe I won't have to. He did it pretty well. I mean, there's not much to complain about. I could fix this while I'm here. Anyway, so now I just have to get rid of that picture. And then I can draw the damn thing. Alright, so the simple thing is he's got a lever. Okay, that's now a catapult. I guess I have to really use a different I have to use a different utensil. Time out. Well, this one isn't perfect either, but it's better. So, alright. And so we put a spring on here as suggested, or, I used a rubber band, but whatever, it doesn't really matter. So when you push it out, spring pushes back. It takes away the problem of the weight of the lever. So now the lever's length and its weight don't make any difference to the experiment. And the simple experiment is you put the half mass out here and the double mass here, and you basically throw them. So this is horizontal, but I'm going to illustrate it as a pendulum going up, and basically all you're going to do is swing these 2 objects into gravity. And the fact is, okay, that if you can get the half mass, okay, to go 4 times higher, okay, than the full mass. Let's make this a 2 just to make it easier, and a 1. Sorry, little details. Try to create less and less confusion, and damn that frickin' pain in the ass. He's just never gonna. I just can't have it go my way, can I? Not really. Not entirely. So anyway, that's the illustration. Good enough. Okay, so we've got 1 unit of distance here, and the idea is you got 4 units of distance here. And that pretty much proves the case. This is what happened when he dropped the clay. The experiment he didn't do, okay, didn't show everybody, is that you drop the 2 mass from 1 unit of distance, and he did the experiment and it compressed the clay the same amount, okay, as the 1 mass from 4, 1, 2, 3, 4 distances, okay. So essentially it's a reconfirmation of that experiment, in the sense it's basically showing that all you need is that in gravity this will be twice the velocity over here, falling from that height, as this object will fall 1 velocity, and you've just doubled the mass. You have a 2 mass here and you have a 1 mass here. So momentum is fine. Momentum says everything is fine. I use the same amount of force. I move this the same amount. The lever, in fact, moved twice as fast here as it did in here, and I essentially have perfectly rational momentum theory and a perfectly irrational kinetic energy theory. Their claim is that this has twice 2x the kinetic energy, and yet it only got 1 unit of force. So somehow it converted the 1 unit of force into 2 units of kinetic energy, which doesn't make any sense at all. So, it's as good as the Mythbuster experiment, certainly, and we'll just have to wait and see if people concede that, yeah, it's more than 1.4, that's for sure. And so I'll play the video because you can see the dramatic difference in the motion of the 2 objects, and so you might as well take advantage of seeing that. And maybe there's nothing much to say, right? I mean, it's just, it's a pretty good piece of evidence for my side. That's about all there is to say. But I'm not going to gloat, because that's dangerous in these circumstances. What the hell just happened? I don't know. This is the camera that's got to go, right? Yeah. I don't know what happened. Alright, this should be the video. Should be. We'll see. That's not the right box. Okay, this is the one. That ain't it either. That ain't it either. Jesus. Which one moves that damn thing? Alright, that was the one. I gotta... it still ain't it. Just click on it down here. Sorry. All this little bits of bullshit you have to go through. What is wrong with the resolution on this? Well, I'll fix that. This is screen thing. Alright, so this should be the right video. So let's play it. We'll just go through the first half because he just explains the setup.
Backed by popular demand,
the height.
The pendulum collision experiments.
Thank you.
Got a spring.
I've been saying this is what you should be doing, is trying these different experiments in different ways, but I'm glad he put the spring on here, so good idea. Get rid of the problem of the lever absorbing any of the energy. So now we've eliminated the lever because it absorbs the same energy theoretically in both circumstances. So it can't play a role anymore. We don't even have to worry about the lever on this side being the same amount of lever on that side. You just have to worry about the fulcrum being secure, blah, blah, blah. Alright, so he just goes through pointing out the height of the pendulum, which is nice to know, but frankly, I don't have to do the math to see it. So, thankfully, it's obvious enough that it doesn't even require any math, frankly. So he's just explaining the starting points had to be a little different because of the fact that the arc of this lever is relatively short lever. The longer you make the lever, the less this would be a problem, but the shorter it is, the more dramatic it is. But anyway, no big deal. You start them from basically the same hitting contact point. And so let's show so this is the 2 mass first, and does a few versions of it.
Yeah. You're going to have a lot of collision loss in it.
Yeah, so he's just explaining.
We'll see how it goes anyway.
Yes, let's do that part. There we go. Okay, so it goes about to the end of the board, you can see it doesn't appear to be any
It's
higher
going up to about the end
than.
of the board, isn't it?
Okay, so I'll try to. You can see it. That's about as far as it gets. It's not even as high as the tape measure. The bottom of it isn't as high as the tape measure, and that's as high as it gets. So it's only like, you can almost say it's, barely an inch and a half or something. Look at it again. You can see that, right? I could blow it up, I suppose. Might as well. Alright, so we'll try that again. So we don't need to see the launching, we just need to see the landing. Alright, so play that again. Okay, see if I can get a better picture. There it is. That's a good one there. And you got to say, that's not very high. I mean, at best, 2 inches, maybe. At best.
Okay, I'll pause you.
Okay.
Right, guys, we got the half mass 2 distances from the fulcrum now. Until the stop, that should swing.
Okay, so I guess I should. Well, how much of this can you see? You're probably going to need to slide this over, so I probably should put it back to its smaller size so you can see the experiment a couple of times, and then I'll do the closing up part again. But it's going to basically fly right off the screen, so anyway, we'll see. Play the video.
At its lowest point in gravity. Here we go.
So it's almost to the edge of the table. Oh, there it goes. Well, I missed it, but went pretty far. Pretty fast, pretty dramatic. Clearly, like Brozo's experiment,
no idea.
We're talking about 19 and 11 kind of results. Pretty clearly not 1.4 results. It's a lot more than 0.4 faster, a lot more than 0.4 further. Alright, so that's a pretty good image of it. So it's above the tape measure. It's going to go a little bit higher. There it goes. Okay, so, I mean, come on. Can there really be an argument about the fact that that is dramatic? So now we'll blow it up again and show you. And move that over. Look at the height difference. So the other one was like here, right? Just a little spot here. All right. In terms of height, not even as high as the tape measure. You're at least 2 tape measures high now, maybe 3. A lot higher. A lot more than twice as high in the gravity. A lot more than twice. So really should be no doubt that clearly this is not confirming the 1.4 theory. 1.4 is out of the question. That's going a lot faster than 0.4 faster. And it's going a lot higher than 0.4 higher, or even twice as high.
An experiment to the level of physicist Michael. I'm not claiming that it...
Okay, so he's not claiming it's as good. Well, frankly, he didn't do this experiment, did he? No. So why make a comparison to his experiment? Because he wasn't even willing to do this experiment. Even though I had mentioned the catapult previous to him doing the lever experiment, because I had already figured out the catapult eliminates the losses to the lever, which makes the experiment much clearer, because all the energy can't disappear somewhere anymore. It has to go into the objects.
It's proof of anything. It's a bit rickety. It's just to, in the
They're all a bit rickety. I don't know why you won't admit they're a bit rickety when they look your way, and then this one you have to point out it's a bit rickety. But yes, all of our experiments are rickety. And isn't that a commentary on physics, that they've never done these experiments non-rickety?
The spirit of...
I mean, look at that. I mean, come on. Come on.
as you wanted, Gary, just to play around with it a bit and see if we can deduce.
Yeah, well, your deduction is that it should be away, but you should be yelling the word inertia at me. Inertia, inertia, it's inertia. You should be inertiating me about how, well, look, see how you can't move the lighter thing faster. You can't do it. You can't throw it twice as fast. You can't do it because of inertia. It's inertia. Remember all that crap you did? Shit.
Anything from it?
Yeah, there's no inertia apparent here. There's no problem launching that thing. I mean, look, even when it's, at just this almost the same distance the other one, it's already, way up in the air, way much higher. So he had to move the board a little bit forward. So this is technically further back because he moved the board forward to account for the fact that the lever is extended further back. So when you retract the lever, you have to put them both at the right starting position. So he did move. So the tape measure really should be reading like 21 here. The end of the table should actually be here. So this is really past the end of the table. That's why it's so much higher. But the real point is it goes 4 times higher. It's clearly
fun as well, isn't it?
Damn close to 4. If not 4, then 3. But it's definitely 3 plus, which is way beyond what the kinetic energy theory predicts. Way beyond.
In a world of not so much fun.
Yeah, so there you go. I mean, dramatic, really. When it comes back and hits, you can see it. Lots of energy. Bang. It's going fast. I mean, no doubt about it.
I suppose whether you could accurately...
Not a 0.4 thing. That's not a 0.4 event. That's not 0.4 more.
You measure the arc. It's probably difficult to tell from your angle.
So he does have this one slightly higher. So it's a ½ higher. So let's recognize that as a truth. It's sitting a ½ higher, apparently, than the other one was sitting. Okay, so when he did the other one, it was a ½ lower to start with.
Sure.
All right, so yeah, that is important. Okay, but I'm just saying ½ inch isn't what we're worried about here. It's a lot more than a ½ inch difference in the final result. I'm just saying, come on. That's 0.4.
It goes a fair old way, doesn't it? See what it looks like from the cameras.
Yeah, way up there that time.
Yeah,
way the hell up there. That one went way over here. Way up there.
Go past, doesn't it?
A lot higher than here.
By the way, when I was doing the rolling wheel experiment...
Oh, see, he's got to ruin the perfectly good video.
There is one video that got on the shorts, because it was under a minute, and I had both wheels the same weight.
Right, I know, but it doesn't matter. You're just not getting it. That anytime you change where the mass is, and then you're going to use gravity to affect it, okay, then the rotational energy, that's what you're really talking about, is how much energy it takes to turn it. All right, because it's going to end up being angular momentum. You have two things. You have the linear motion, and then you have the angular momentum. And frankly, gravity isn't your friend on either case. In either case, it's not going to be linear.
But different radius.
Annoying. I've made it clear what my qualifications of the argument are, so I don't know why you keep bringing it up, but I've made the argument over and over again. It's just about whether or not you're consolidating the weight. The lots of weight here is the same as a little bit of weight out here, just like the lever. It's exactly the same argument as you're demonstrating right here. It's the same thing. Twice the velocity out here of a half mass is the same as one velocity here with a one mass, and the wheel will store the same energy. If I make a flywheel and I weight it like that, the two flywheels will function identically. because they can't tell the difference. All they know is what's the matter, what's the average piece of mass doing, what's the average velocity of the average piece of mass. That's all that's going to matter to how much energy it takes to spin the wheel, or how much force it takes to stop the wheel. And you just keep playing with gravity. It's, you know.
Gary, if you wanted to have a look at that one.
No, I saw it, and I way up there. So,
I don't know
all right. So
how much more we want than that. And I don't know whether it's any use to anybody.
I'm just saying, how could I mean, it should be apparent to you doing the experiment that, gee, that looks like a lot more than 0.4. I mean, it only has to be 0.4 faster. Anything over 0.4 faster, and your theory's in trouble, right? Right. Looks like a lot more than 0.4.
Okay.
Certainly a lot higher than twice as high.
See what you think. Bye for now.
Okay. So.
Back by pop.
All right. So that's the video. Looks like good news from my side, frankly. So that's all we'll say. And we'll see what other people make out of it. Well, I guess we could check, but I'm sure the morons aren't saying anything useful. Let's see. His reply is, do you reckon you can calculate anything, John, or do you need a better data? So, in fact, the only thing we need to know is the difference in height of the probe. There's no difference. It's a ½ inch difference. Okay, the equation V equals the square root of 2gh tells us the velocity. It doesn't tell you the height, and the height is the thing that's really telling you the story. So the height it travels, by the way. I mean, obviously gravity is not a height dependent force, so you know they can keep saying it, but no, it's about time, not height. All right, so he goes through this crap, and let's see, energy equals 1/2 mv squared, so he just keeps saying the same shit. In the previous experiments where you let the probe swing by hand, the height is easily measured. But the experiment here, the horizontal distance will do, but because we know the height of the wire r, so he just keeps saying it, the same shit. And so he says, possibly there is a recurring factor, like maybe 2 times the square root of 1/2. I don't even know what this even means. 1 kilogram versus 1/2 kilogram with 17 and 24. So who knows what he's saying. The fact is, you can see the height is not insignificant. Okay, again, I'll just say it's obviously more than 3 times higher, and I'd say it looks like 4, and that's exactly what I would have predicted, of course. So I don't know how they can convert it into anything else. I mean, you can look at it again yourself. I mean, let's put the image back on to get rid of this, and put the image back, and we can probably blow it up a little bit. Oh God, apparently I can't. Oh, there I can. Blow it up a lot of bit. There. All right, so I mean, you know, this is the height difference. I mean, you can't see my mouse, but okay. So right right there, way up there, to all the way down to the board over there. You can see the board is under here. Oh yeah, well, under there. And then you got this little tiny height, a little tiny height where it's just the shadow. You can see its shadow. You know, not very high, very high. Seems obvious, but it's bad camera angle. Blah blah blah. Lots of things can be said, but it seems pretty clear it's real height difference. All right, so that's enough. No point in going on about it. Maybe he'll do the experiment again with just filming it from horizontally, so it's easier to see the height difference. And we'll see. But anyway, looks good to me, frankly. So till the next time and such.